I've been to see with too many people in this room. It's going to come. It's going to happen. Okay. Okay. So I'm going to talk to you a little. I mean, first, thank you for Mr. Trowbridge for your introduction about the importance of plankton, because what I'll talk about is related to this, and many of us are going to relate to this as we go. So the topic of my talk has to do with the color of the water. I'm one of a few, about 300 people in the world that study that, and one of a few of them that are also colorblind. but which means that we're very sensitive to the numbers more than we're sensitive to our eyes. But we can mistake red and green sometimes. Anyways, okay. So some of you will recognize this. It's in New Zealand, but what you're seeing here is it's a signal measured by satellite, VIIRS in 2015, as observed if a human was on that satellite. And what you see is all these swirls coming off, some of them collected to land on both sides, and they obviously have different color, different intensity relative to the water around them. And the idea of using color to study biology in the ocean has to do with the simple fact that from a satellite you see the whole ocean on a daily time scale, and with pixel size that nowadays can go down as low as 10 meters on a regular basis. And that means that you can really, if you can interpret the signal, you can say something about biology on the time scale in which it occurs. Phytoplankton divide on the order of once a day. And if you go with an expedition, for a month and you come back, you don't capture the whole dynamics that have to do with their development. So we look at color and brightness. We look at sources and sinks. So you can see, for example, that there are some rivers on this side of the South Island in New Zealand that is releasing stuff into the water. And we're trying to understand what it tells us about processes. So I'll start with a little demonstration, which I do with kids, and I think of myself as one of all ages, which simply has to do with when you see a certain color, what does it mean in terms of, does it absorb the color, does it reflect it, does it let it pass through? So I have a simple LED here, and I have water that's colored in green, red, and blue. And I'll start by just polling the audience with respect to, if I shine this through the blue water, would the blue go through? Will the blue be absorbed? What do people think? I mean, let's vote for those who think that the blue is going to get absorbed by the blue. We're getting, excellent, we're getting 5 people. How many think the blue is going to go through? Maybe 8 or 9. The other ones are too shy too. Okay, so is it going through? Yes. Okay, so the color you see is the color that's not absorbed. Okay, so when you see that plants are green, that means that the molecule of chlorophyll, which is the molecule that takes sunlight and turns it into organic energy that feeds the whole food chain, is not absorbing green, but absorbing the blue and the red. So we talked about absorption. Then there's something else that happens with light, particularly if you look from a satellite. So you look at it from a satellite to the ocean. For you to see light changing, something in the water has to change the trajectory of light. So can you see the beam? You see the beam? Or you see the point? So, I mean, it tells you a variety of things. One of these is that they lie you in all these science fiction movies. You'll never see the beam in between the two spaceships. Because if there's nothing in between us, there's no reflection of light towards your eye. You'll see the spot maybe on the other spaceship, but you're not going to see that. So in order to see the beam, you need something to reflect the light to your eye. So let's try water without anything in it. Can you see the beam? Yes. You see the beam? Or you see the dots at the end? Okay. So now let's add into it something called, we like to use Maalox. You can use milk, but we like to use, it's an anti-acid. It's something you get when you have an acid stomach. It just does a good job in doing something that sediments do, or phytoplankton as well. Can you see the beam better now? So in order to see, in order for light to come back to satellite, something has to reflect the light of the sky. So it needs not to get absorbed by the water, and then it needs to be reflected back. And in addition, we have something else that happens with the chlorophyll molecule. So I have chlorophyll here extracted. And I'm going to ask you, so chlorophyll is green. Can you see the green? I don't know if you can see the green.
Yeah.
You can see it pretty well. Okay, so now I'm going to shine blue light into it. What do you see towards your eyes?
Green.
Do you see green or do you see some other red?
Red.
Do you see the red? The red reflected. Yeah. So this is what we call fluorescence. The blue is absorbed by the chlorophyll molecule and it fluoresces in the red. And this allows us in the ocean to put instruments on a variety of platforms that shine blue light and measure red light coming back. And that signal we know is only from chlorophyll molecule, nothing else does it. And so we use it to quantify in the water how much chlorophyll there is, and even from satellite we can see fluorescence, which is amazing because it's the only signal coming back from the ocean that we know 100% is only from phytoplankton. Other things reflect, other things absorb, but only chlorophyll fluoresces when you, in the red when you shine on it from the blue. Okay, so let's move on. So we talked about, this molecule, the chlorophyll, is something that's ubiquitous to all these phytoplankton that you hear a lot about today. And one thing that's really amazing in them is that it's a family of many, many different kind of organisms, some of them not related to each other. Some of them swim, some of them are mixotroph, they mean they eat as well as photosynthesize. I mean, think about swimming plants. We don't have anything on Earth that are plants that move around. Some of those can swim. Some of those are responsible for carbon going down to depth. Some of them fix nitrogen, meaning that they fertilize themselves. All kind of, I mean, they're involved in many, many things. As you heard before, they're the reason of half of the oxygen you breathe came at one time or another from phytoplankton. They're tremendously important. What you see here is a compilation of 10 years of a satellite called Voyage that NASA launched. But what we're looking here is a product derived from it, and the product is the concentration of chlorophyll in the water. So you use the signal in the satellites to then tell you something about the concentration of phytoplankton. And what we're observing is really a breathing planet. These are the areas where oxygen is produced, the areas where CO2 is taken down. We can see season, we can see El Nino, all of this stuff. And so, again, being able to see it from space, we can really make a story about the process that's happening in the ocean. So, where does Plankton, Planet, and Tara fit in? In order to come up with algorithm, we need to do measurement in the ocean at the same time as satellite pass overhead, and either validate algorithms that already were derived or get new data to improve algorithms as we increase the capabilities of things we can do from space by adding more wavelength, adding, changing scales, things of that nature. There's a lot we don't know about the ocean. So these are the unknowns. And so every time we use a different technology in the ocean, we learn something we never knew before. It's like having new glasses. And so I really see, and I've been working with TAR since 2009, and Plankton Planet as a real opportunity to get data on a global scale that we can not get in any other way. So in terms of where are we moving with this technology? I'm the lead of a science team for a new satellite called PACE that Trump would like to get rid of, but so far Congress doesn't let him. Get rid of it. And what it will have is UV capabilities, which so far we don't have on any of the ocean color satellites. It will have very narrow bands, every 5 nanometers, so we can not only look at chlorophyll, we can separate other pigments that are there and then link them to different phytoplankton. It's going to have, we're still not sure about polarization capabilities, which means that we can, and you'll see it with the microscopy, we can have different direction of light that we can filter in different ways that, again, increase the information content of the signal that's spaced. And then there's new satellites. There's Sentinel-2 from Europe that has a 10-meter footprint. Landsat-8, 30-meter. We're now using it in Maine to site aquaculture, oysters in Maine, because as in New Zealand, we have a very long coast with a lot of fjords, and the only way we can sample every nook and cranny in it and then pass the information to people who don't do aquaculture is from space, instead of doing by trial and error. Also using LiDARs. LiDARs are lasers from space that we're sending, and we're looking at a signal as a function of time, and this gives us depth resolution. I did not tell you, but what we're seeing from space is only the surface with an integration of the signal coming from the surface. With LiDARs, you can get information that's depth dependent, so you can say something about that. And so we also hope to improve algorithm by not just using the data from light, but adding in information about temperature. And by adding Plankton, Planet, and Tara data, we can look at breaking the signal into the components. Which are the phytoplanktons that are there? Not just that there's a lot of phytoplankton, there's less of it, but who actually is the dominating species? And this is moving to the next lecture by my friend Mick, who's going to...
No, the next one
it's not the next
will be David Group.
but it will link to it.
That's right.